Hi. Now what we have here then is that a website receives hits at a rate of 300 per hour, and we've seen that this means that the number of hits follows a Poisson distribution. Now we're told that the website will go down if there are more than 70 hits in 10 minutes, and using a suitable approximation, what we've got to do is find the probability that the website will go down in a particular 10-minute interval. So if you haven't tried this already, would like to give it a go, just pause the video, come back when ready, and I'll run through the work solution. Okay, welcome back if you had a go. So let's just see how we'd approach this problem. Well, we know that the number of hits follows a Poisson distribution, and we're told that they occur at a rate of 300 per hour, and we're now looking over a 10-minute interval. So a 10-minute interval is 1/6 of an hour. So 1/6 of 300 is 50 hits that we would expect every 10 minutes. So the first thing I'd want to do is define a random variable. Let's say we call it x. Let x be the random variable, RV for short. Okay, and this is going to be the number of hits that we can expect per 10-minute interval. Okay, and we know that we can have this as x following a Poisson distribution with a mean of 50. We're expecting 50 hits every 10 minutes. Now we're asked to use a suitable approximation, and we can, providing the mean is greater than 20. That generally tends to be the limit that we use, although I've seen it differ in from different exam boards, different textbooks, but I've seen it go down as low as 10 actually. But here I'm going to say, since the mean lambda is greater than 20, then what we can say is that our random variable x can be approximated to another random variable y which follows a normal distribution. And for a normal distribution you have two parameters, the mean and the variance. Well, the mean is 50, okay, and the variance for a Poisson distribution turns out to be exactly the same as the mean. So the variance is the same as the mean. For this example, it's going to be 50. So we've got to look at this distribution then, okay? So if I was to sketch our normal distribution, we'd have something like this. We'd have our random variable here, which is now going to be y. It's got a mean of 50. And below this, I'd want to sketch our standardized distribution z. Z is a normal distribution, follows a normal distribution with a mean of 0 and a variance of 1. Now, we're trying to work out then that the probability that the site will go down. So let's just put this in first of all. The probability the site will go down. And when does it go down? Well, we're told that if the number of hits are more than 70, so that's going to be the probability that x is more than 70. But we've seen that this random variable x that follows the Poisson can be approximated to this random variable y. Okay, so that's going to be exactly the same as the probability that y is greater than. Now we've got to be careful here because, okay, we might have 70, but this is for x. And when we are changing a discrete random variable to a continuous one, we're approximating it to a continuous one, think of it as made up of rectangles like this of unit width around our observed value. So this value here would be 70.5, and because we're wanting the probability of being more than 70, we want to be to the right of 70 but not include it. Okay, so it'd be this section here. this value would be 70.5. It's called the continuity correction, and if you're unsure of this, I've got tutorials on my website ExamSolutions.net on this. Continuity corrections, just look it up in the index. If it had been the case of x is greater than or equal to 70, then I would need to include the 70, and so therefore my shaded region would go right the way back, include the 70, and go to the far side of this box here. So with this value here would be 69.5. So it would be y is greater than 69.5 if that were the case, that x were greater than or equal to 70. But it's not. We're wanting x to be greater than 70, so with the continuity correction it's y is greater than 70.5. So a place to take extra care on. Now from here on, if we were looking in our tables, okay, we need to convert this to find out what the equivalent standardized value z is going to be. Remember that z always equals the observed value, which the observed value up here would be a little y, minus the mean all over the standard deviation sigma. So therefore z for us in this example is going to be the observed value, y, well that corresponds to 70.5, minus the mean, mu, which is 50, and that is divided by the standard deviation, sigma. That's the square root of the variance, and the variance was 50, so we need to divide that by the square root of 50. Work that out on your calculator, and what you get is 2.899, and so on. So the probability that y is greater than 70.5 corresponds to working out this area here, which is the probability that z is greater than 2.899, and so on. Now normally most tables work out the probability of being less than the value z. Well, knowing that the whole area, which represents all the probability, comes to 1, we can regard this as 1 minus the probability that z is less than 2.899, and so on. So when you look this up in your tables, you'll find that you get 0.9981. Okay, and then if you subtract that value from 1, you end up with 0.0019. Okay, so that's the probability then that the site will go down, using a normal approximation then to the Poisson distribution. Don't forget your continuity correction though, so important. Alright.